So previously, we have introduced the concept of overpotential, electrode overpotential, and we also um, introduced the concept of polarization curve, which is the current density versus overpotential for an electrode or half-cell reaction. But how exactly to get such so-called polarization curve from theoretical point of view? Here we introduce the Butler-Volmer equation. Butler-Volmer equation. And it is one of the most important equations for electrochemistry. And let's first look at it at a simplified condition, which is, read to yourself, without mass transport limitation. Let's first take a look at a one-step electrode reaction, or we say half-cell reaction, but without mass transport limitation. Without mass transport limitation. Typically, mass transport is to bring species to the reaction site and bring products away from the reaction. And sometimes these mass transport can limit the reaction rate. But let's first look at the case without any limitation from mass transport, which means the bringing of species to and from the reaction site is very, very fast. And you can achieve this typically by stirring, active stirring, high gas flow rate if it's gas, involves gas, and you can also achieve this by keeping the current, which is reaction rate, at a low value. But anyway, for situations, simplified situation without mass transport limitation, let's look at this simple one-step electrode, the half-cell reaction. Oxidized species OX plus electron, N electron to form reduced species. This is generalized. We don't know what the oxidized species is, what the reduced species is, but it's okay. And we know the number of electron transferred is N. Okay? For such an electrochemical half-cell reaction, this is half-cell reaction because only one species is got reduced, OX got reduced into RED. Okay, without mass transport limitation, the Butler-Volmer equation gives the net current density, J. J for current density, which is essentially current divided by the area. Net current density, or the overall current density, would be a function of total overpotential for that electrode. Overpotential for that electrode reaction or half-cell reaction. And the Butler-Volmer equation just describes mathematically the relationship between J, net current density, and eta, which is overpotential for, read to yourself, that specific electrode reaction of that specific half-cell reaction. And eta, as we said before, would be the potential, actual potential for the redox reaction minus the equilibrium potential for that redox reaction. That's our potential. Okay, the difference between actual versus equilibrium for this redox or half cell reaction. And then the equation goes something like this. J, as we already said, would be net current density, and it comes from two parts, JA and JC. A for anodic, C for cathodic. So the overall or net current density is coming from the summation of both the anodic and the cathodic part of that half-cell reaction, which is very important concept for any reaction. Actually, in here, for any electrochemical reaction, at any moment, there's always species that got oxidized, while at the same time, there are always species that got reduced. But the overall reaction rate represented by this net current density would be the summation, the total between the anodic or the so-called oxidation going from LED to OX plus the cathodic or the reduction going from OX to LED. The net reaction is a summation of these two parts, anodic and cathodic, oxidation and reduction. And for each of these terms, the anodic would be the first term here, exponential, bracket 1 minus beta. Beta is what we said a symmetry factor. We're going to talk about this in greater detail later. N would be the number of electrons transferred. F would be Faraday constant. Eta would be the, as you know, over potential for that specific electrode reaction. The difference between actual potential for that half-cell reaction and the equilibrium potential for that half-cell reaction. And RT, of course, you know, gas constant and temperature in absolute scale. This term would be correspond to the anodic, and this minus exp minus beta NF eta over RT gives the cathodic portion, and beta, as we said, would be the symmetry factor, eta over potential, N the number of electron transport, and RT. Okay, so again, as we said, Ja would be anodic or so-called oxidation part current density, and it is, as you can imagine, in the unit of amps per square centimeter quite often. Jc would be the cathodic going from OX to LED or reduction current density, also in the unit of amps per square centimeter. Ja going from LED back to Rx. And J0 would be in front of this overall bracket would be so-called exchange current density. It's a constant for a typical electrochemical half-cell reaction. Okay, and it also in the unit of amps per square centimeter. Beta, as we explained, would be symmetry factor, unitless. We'll explain beta symmetry factor in greater detail later. It essentially tells us the shape of the energy barrier between oxidized species side and reduced species side. It also determines the shape of the so-called polarization curve, this J eta curve. R, as we said, gas constant. T, absolute temperature in Kelvin. Okay, this overall would be the Butler-Volmer equation. But remember, this is for the special condition that read to yourself without mass transport limitation. Without mass transport limitation. This is, as we said, the assumptions for this important simplified Butler-Volmer equation, assuming, read to yourself, uniform concentration, which means the concentration for reactants and the products are all the same throughout the electrolyte-electrode system. Okay, and how do you achieve uniform concentration or achieve the situation that you say, oh, there's no mass transport limitation? You do that typically by extensive stirring. If you are in a solution, extensive stirring, okay, using magnetic stir bar or some other mechanism to actively stir the system. For gas phase, you are going to blow hard, introduce high gas flow rate to force the convection. At the same time, another possibility would be to keep the current relatively low. How low? We'll talk about it. But keep the current or current density low, which means you are not consuming a lot of the reactant. At the same time, you are not generating a lot of reactant. Then, combined maybe with stirring, you can make sure there's no mass transport limitation. And under that condition, we can use this so-called simplified Butler-Volmer equation. And as you noticed about sign convention, as you see, for both current density and for overpotential, for both current density and overpotential, the anodic or the oxidation would be designated as positive. here the first term within this bracket corresponds to the anodic, and you can see this because of the exp term, this whole thing would be positive, which means with positive eta or over potential, the anodic current would be positive. And the cathodic part, which is reduction part, corresponds to the second term. And don't forget, there's a minus sign in front of this exponential term, but it corresponds to plus of Jc. So the cathodic term would be designated, the current would be designated as negative. Similarly, eta, if it's negative, it would be designated as cathodic over negative overpotential corresponds to cathodic overpotential. Okay, so that is a sign convention for both eta. If eta is greater than 0, which means the actual potential is higher than the equilibrium potential or more positive, and of course, as you can imagine, if it's the actual potential is more positive, then it has a tendency to be oxidized. That current, anodic current or oxidation current, is also what we say positive. On the other hand, if eta is negative, which means the electrode potential is lower than equilibrium or more negative than equilibrium, then eta would be negative. And as we said, eta would be negative, and the half-cell reaction is going through reduction, and the cathodic current, that minus sign in front of this, is designed as negative, and the overall current is also designed as positive or anodic if it's positive. If it's negative, it will be cathodic or reduction. Okay.